mine at this. But fortunately for both of us, had scheduled a sabbatical or year visiting Duke just after mirror symmetry was discovered, so he and I got to have a great, fun year trying to figure out what physics was all about together. Anyway, Sheldon.
Okay. Well, thank you, Dave, for the introduction. That was a fun year. I'm still trying to figure it out, but I'm still having fun. And thanks to the organizers for the invitation to speak here. I'm going to talk about a paper that's a year old now on elliptic vibrations with Albert Clem and Wang. Also, about half the talk will be about work in progress on just things that we've discovered since then, and that we certainly understand this a lot better than we did when the paper first came out. So start with elliptic vibration, and we're talking about elliptically fibered Calabi-Yau threefolds. And for definiteness, I'm going to focus on the base P2, which is the simplest case and has almost all of the features anyway. And one of the examples that happened this wonderful year that Dave was talking about, there's a realization of this example as a weighted hypersurface. So I've been asked to try to make this, intelligible to both mathematicians and physicists. So I'll use the simpler Green-Plesser orbifold construction here in describing the mirror symmetry. We have a weight 18 hypersurface in weighted projective space with weights 1, 1, 1, 6, 9. And to go ahead and make this into a Calabi-Yau, the singular locus is when x1, x2, x3 are 0. There's an orbifold singularity. We blow it up. And then after blowing it up, the projection to the first three coordinates becomes well-defined, giving a map from the Calabi-Yau threefold to P2 and exhibiting the elliptic vibration structure. So this can also be described by Baturov's mirror construction, which we do in our paper as well, and our work of Hosano, Clem, Tyson, and Yau did this as well by the toric construction. So to describe this as a two-parameter model, we have the H11 is two-dimensional. We have two Kähler classes, and they can be parametrized most naturally by generators of the ample cone or the Kähler cone. So we take a line, a hypersurface in P2, pull it back to the Calabi-Yau, and we call that L. The other divisor that we naturally have is E, the exceptional divisor of that blow-up. E is not an ample class, but if we take H equal to E plus 3L, that is an ample class. H and L together generate the Kähler cone. The dual curve classes, which generate the Mori cone of effective curves, are generated by the fiber class, which I'll continue to call F, and the class of the line. And one feature of this is the line I'll refer to as being in the base, but more precisely, it's in the section. So the section by projection is identified with P2, so I could talk about curve classes in the base as living directly inside the Calabi-Yau threefold. That's the geometry I'll be talking about here. Okay, so for the mirror, I'll describe that by the Green-Plesser orbifold construction. So the Calabi-Yau being two Kähler parameters, the mirror has two complex structure parameters, which will be parametrized in a multivalued way by psi and phi. Here's the hypersurface G as a finite group of roots of unity, which I won't make explicit here. So because of the action of roots of unity, there will be some rescalings of the psi and phi. So those are those symmetries are right there. And there's also another symmetry, which is most easily seen by toric geometry, is that if I go ahead and rescale psi to omega, and I move them around in this way, I get isomorphic Calabi-Yau, an isomorphic Calabi-Yau for this mirror. So the moduli space of the mirror is a two-dimensional toric variety with certain coordinates. The coordinates, at least at large complex structure or equivalently maximal unipotent monodromy, are some combinations of the phis and the psis. And then if we wanted to do mirror symmetry to compare these to the enumerative geometry or the topological string amplitudes of the original Calabi-Yau, we use flat coordinates, the coordinates parameterizing the Kähler classes, and then we have Q and Q tilde. And I'm doing something that's would have been very unusual back in the day, but is very natural now, because these are the natural coordinates to use in classical mirror symmetry. So we're not using classical mirror symmetry here. The modularity is not seen in these coordinates. So we're going to be shifting coordinates to see the modularity. Okay, and that came here in this paper. Many people have seen this shift since in other ways. And more generality is that if we combine these coordinates in a multivalued way, these are the coordinates at large radius, to a new variable, that here we have periods, we have monodromies, physical monodromies of the periods of this Calabi-Yau threefold, which acts as an SL2, where the S generator and the T generator change the sign of these equations. So the divisor is fixed, but the equations change by a sign. And this sign change is going to be important. If Greg were giving this talk, I would have had something cute here to remember this. You must remember this later. So we're going to see this shift, we have to go ahead and shift coordinates to see the modularity. And this multiplier system, in the language of modular forms with multipliers, it's exactly the same as the multiplier system of eta to the 12th. So this is going to be important later, is that if we go ahead and take eta to the 24th as delta, that's an honest SL2 modular form, but if we change by the S transformation, the T transformation, we pick up a sign, but the ST transformation is well defined. It leaves eta invariant. Okay, so in these shifted coordinates that we go ahead and take the eta to the, eta to the, I'm sorry, I didn't understand the question. Right, so I'm just taking it in terms of generators. So I'm saying that if I go ahead and I put in A tau plus B over C tau plus D and use the generation of SL2 by these two transformations, you get everything. So this is just I'm writing a concise way to do that so I don't have to describe the whole multiplier system, but it is this one. Okay, so then when we go ahead and shift coordinates, this t plus 3/2 tau is the logarithm of that relation q equals little q to the 3/2 q tilde. So this is our change of coordinates in this new basis. T is a divisor class. It's not a Kähler class, but it's the one we want. And the thing we've understood since then is how to really see this. This is seen in the B model traditionally. Now I can see this directly on the elliptically fibered Calabi-Yau using homological mirror symmetry. So we'll see the SL2 acting on the derived category directly. So, a topological string partition function is what we're interested in. I've used the Gromov-Witten language, but I could be doing the Gromov-Witten partition function, the stable pairs partition function of Pontryagin-Thomas, the normalized Donaldson-Thomas invariance, your favorite way to go ahead and think of this, or just the topological string partition function. This is the object I want to understand in these variables. So, in the good variables that we have, I've already shifted, and I'll keep on using Q. That's why the tilde is now off. These are the variables I want, not the large radius variables. Q is the usual exponential of 2 pi I tau. Capital Q is this, and lambda is just Z is just a multiple of the string coupling to go ahead and match the theory of Jacobi forms. We factor out the degree 0 in the base contribution and express everything else in powers of the base degree. All the fiber degree is contained in here. So what ZD contains is topological string amplitudes for all classes of all genus where the projection to the base is degree D after correcting for the degree 0 term, after factoring out that contribution. And our claim, just to repeat that so you can see it, is that this quantity is a weak Jacobi form of weight 0 and index D times D minus 3 over 2 with multipliers in the sense that I said before. That's the main claim, but more precisely is that we can go ahead and give a finite Ansatz for this form. So the denominator is a fixed form. This is a fixed Jacobi form. Eta is known. This is a weak Jacobi form of a certain weight and a certain index. I'll define weak Jacobi forms in a second. And the point is that this lives in a finite dimensional vector space. So we've reduced the entire topological string amplitude, at least at degree d, to a finite problem. And I will say that there was a time when we were really hoping that there would be no limit to how far we can take d, but sadly that's not the case, and the field is still open. Okay, and so this is not the first time Jacobi forms came in related situations. So the elliptic genus of E strings has been studied the last few years by Hagigat, Lockhart, Vafa, Kim Lee, Park and Vafa, and Kai, Wang, and Sun. And then in Hagigat, Clem, Lockhart, and Vafa studied this in six-dimensional superconformal field theory. In a related situation, these came up. So that's a part of a motivation as a consistency check, is that we have the in the holomorphic geometry, all you see are holomorphic expressions, which are not modular necessarily, so we'll see E2. If we replace that by the almost holomorphic modular form E2 hat, where tau 2 is the imaginary part of tau, and we take the z and replace it by its non-holomorphic part, of which this is the holomorphic limit, then this, just assuming that the partition function is expressed in this way as a Jacobi form, automatically implies that, that this satisfies the modular anomaly equation of William Scheidegger, Yau, and Zhou. So this is a nice consistency check that the Ansatz automatically satisfies the fiber version of the holomorphic anomaly that had been studied before. And in the recent work, the new stuff that's not yet written up, is that we can now derive the modular anomaly equation directly from the wave equation, wave function version of the holomorphic anomaly equation due to Witten. So Min-Shin will talk about this, so I'll be brief on this subject. Okay, so just quickly, what Jacobi forms are is that we have two variables. We have a tau variable and an elliptic variable, which lives modulo the lattice given by 1 in tau. We have SL2Z transformations, and Jacobi forms act in this way. So K is the weight, and M is the index. So weight 0, this term is gone. It's just a modular form. So you already know lots of Jacobi forms. We have Fourier expansions because we have periodicity both in tau and in z. So Q we've already done, that's e to the 2 pi I tau. We have a Fourier expansion there. We similarly have e to the 2 pi I z. And you'll see, remembering that 2 pi z is lambda, y is e to the I lambda, e to the I lambda, which is exactly the parameter of Donaldson-Thomas theory or stable pairs theory. So this is the same change of variables that you would know if you're doing enumerative geometry, and it's the same one that comes up in the string setup. So a weak Jacobi form is that when you go ahead and write this in terms of the Q variable, it stays holomorphic. So this is a condition at the cusp. No condition on Y, but we have a condition at the cusp in Q. That's a weak Jacobi form. Phi minus 2, 1 I just wrote down. This is a well-known Jacobi form of weight minus 1 in index 2. Another one of weight 0 and 1 is half the elliptic genus of the K3. And the basic result here is that the weak Jacobi forms form an algebra bigraded by weight and index, and the algebra is freely generated by E4, E6, phi 0, 1, phi minus 2, 1. Which means that if you go ahead and just pick a weight and an index, there's only finitely many polynomials in these expressions you can write. So that automatically proves that the space of Jacobi forms of a certain weight and index are a finite dimensional vector space. Okay, so let's look and see what this means for d equals 1. So phi 1 of tau z was supposed to have weight 16 and index 0. Index 0 is a modular form. So we're just looking for modular forms of weight 16. There aren't many of those. It's a two-dimensional vector space. So what we have to do is to find this partition function is it's just determined by two invariants, two geometric invariants. Just calculate two numbers, you know the whole partition function for every curved class, every genus that projects to a line. So this is very powerful. very powerful. And so here, let's take this class. It's, let's go ahead and look at the curve class in the class of a line. The lines in P2 are themselves parameterized by P2. So the invariance in these BPS theories if the parameter space is smooth, it's a signed Euler characteristic. The Euler characteristic of the parameter space is 3. So there's one number. And the other number is to go ahead and look at the class of a line plus a fiber. So if we have a fiber, the fiber must meet the section at a point. The line must pass through that point. So for each fiber, in other words, the fibers are parameterized by P2. Maybe I should draw this here. Here's my E. Here's a fiber. And the line has to go through that point. The line is parameterized by a P1, given the fiber first. The fiber is parameterized by P2, so at least up to computing Euler characteristics, it's as if the topology is P2 times P1, and the Euler characteristic is 6. This is odd dimensional, so we change the sign. So that's the calculation. So the invariant is minus 6. To go ahead. So we've computed two numbers, and that tells us what phi 1 is, which tells us the entire enumerative geometry or topological string partition function at degree 1. So infinitely many numbers. And I want to make some observations about this. Even this result has no mathematical proof. Even this simple result, this just there's a lot of genera to go ahead and compute. It just goes way down that way. So I know, Jim Bryan has reduced the proof of this one case to a conjecture about Barron functions that are used to go ahead and compute numbers, invariance, and symmetric obstruction theories. So that's the best result to date on verifying this. The other thing I want to verify is that there are lots of zeros. Just mentioned lots of zeros. 0 is a number, right? So you can go ahead and express 0 as a condition in many of these problems. So this I refer to just coming from classical algebraic geometry. I call this the Castel nuovo band in honor of Castel nuovo's work on bounding the genus of space curves in P3 in projective space. So what we can have is that for each degree, for each homology class, we have a bound on the genus, and that's going to be important for us. Question? Say again? Yeah, this is a proof. I have a proof of that. And it's not quite the Castel nuovo theory, because in the problem the Castel nuovo was interested is finding the bound on the genus of a smooth plane curve. Here, to have contributions to BPS invariance, we just have connected curves. So there's a complication where we go ahead and have to take curves and fit together. But the answer is actually very simple. The maximum genus just comes when the curve projects to a line as a multi-cover. So that's not hard to prove, and that's maybe not surprising. Okay. Then, these numbers, I computed 3 and minus 6, but this is an easy pattern. This just means that taking a line and a certain number of fibers, well, the fibers, picking a certain number of fibers, just picking endpoints on P1. So we're just going to get a sequence of numbers with a factor of 3 for where I stick that fiber, where I put the line into P2. So lots of these numbers are easy to verify. Okay, then just to show how things get more complicated very quickly, is if we take degree 2 now, we have weight 32 and index 4. So already we have a 17-dimensional space of weak Jacobi forms of weight 32, index 4. And now here's where I'll just mention all the ways that you try to solve this problem. So we need 17 constraints. So enumerative geometry, it turns out that enumerative geometry could be made to suffice in this case with hindsight. That wasn't how we originally did it. Holomorphic anomaly, the conifold gap condition, and invariance under this involution I. There were many more than 17 constraints doing it this way. and yet they're not overdetermined. They just point to exactly one solution, which is a good check. Using Zagier's notation for weak Jacobi forms, phi minus 2, 1 is just faster to write that A and phi 0, 1 is B. Here's the answer. Okay, so this gives all the invariants, topological string amplitudes, which fiber over degree 2. In all numbers of fiber wrappings are encoded in that formula. And again, here are many tables. They just go on for a while. Again, you can see the Castel nuovo bound here. And you can see many of these things are easy to see from geometry. The space of conics in P2 is a P5. The signed Euler characteristic is -6. In fact, all of this infinitely many numbers down here can be found by enumerative geometry. This is illusory. So one thing about the Castel nuovo bound is it's asymptotic. There are exceptions in low degree, but here you start to see that you get a slope of 2. And so the true Castel nuovo bound is going to be a pattern coming from here and going down forever. So there are infinitely many numbers over there that you can see. And the reason for this is that these curves, the base curves have genus 0. In the base curve genus 0 case, it's a little bit easier. So this is really going to be the last case where we could really solve the whole problem just by enumerative geometry, modulo the Ansatz, of course. Okay, so using these same techniques now, just here we absolutely need the physical techniques to go ahead and do the computation. We can find phi d for degree up to 7 now. And we expect our methods to work in principle for d up to 20. So we haven't done that. I don't intend to do it. But what do I mean by that is that we have found all these conditions, and they give independent linear conditions on this finite dimensional space of forms. And we have discovered in the process of this that sometimes we do have conditions are dependent. And we think we've computed enough that there are no more surprises. And there's the rub. So assuming that there are no more dependencies on our equations than we've found so far, this method will work up to degree 20. But it can't work beyond that. So we need to find more inputs to go ahead and fix that. So that's the obstacle for solving the topological string. So by doing this, just to emphasize what this does, we have all degree up to 20, all genus, all numbers of fiber wrappings. So while we haven't solved the topological string, we have infinitely many curve classes in all genus. So that this is still pretty powerful result. Also, I'll defer to Minshin's talk without knowing whether or not it's actually in there, is that you can also go from the amplitude z to go ahead and the connected amplitudes fg and rewrite things in terms of fg and use some recursions from the modular anomaly equation to go ahead and get the genus up to 189 without restriction on the base degree. But we can't go G and D infinitely. You just have a choice for how to do this. So that's, again, when I say expect, assuming that there are no new surprises, the method will work in principle to go ahead and compute these. So that's, I think this is a record so far. Okay, so the computational methods is the Castel nuovo bound I mentioned briefly before, and here's the bound to answer Queen's question, is that if you have an irreducible curve class of base degree D and fixed fiber degree E, the maximum arithmetic genus you get is given by this formula. And so here, I guess there's a omission here. This is I wrote E positive, this is E sufficiently large. This is the asymptotic Castel nuovo formula. Okay. And what this is the genus. If you take a curve of degree D and if you take a line, the inverse image of the line is an elliptic ruled surface over the line. And then inside there, you can control, there's a section, there are fiber classes. Now you're doing divisor theory. So you can use divisor theory to go ahead and compute the genus of a curve, which is d times the section plus e fibers, and it's this. So that's how we do that. Okay, another input is after adjusting by eta to the 36d, this is to go, remember our coordinates, our amplitudes are not well defined, they have sign ambiguities. So to go ahead, it's convenient to go ahead and convert to what we call PGD, that these are now regular in the B model away from the discriminant locus in the mirror moduli space. The invariance under I mentioned before, this was studied by Yau and collaborators in other works there. And the conifold gap condition, which controls in the right coordinates that we have a pole coming from supergravity analysis in FG. So from these, I think that's our bag of tricks right now, and that's just as good as we can get. So if anyone has new ideas on how to get further and other conditions we haven't seen, maybe we can get to degree 21. Okay, so generalizations now. So I used P2 to illustrate, but I want to give a little bit more sense of the structure. So let's take an arbitrary base. For now, let's suppose there's a unique, well, certainly for now in this talk, I'm not going to do more than this. Let's take suppose we have a unique section, and that the fibers are irreducible in codimension 1. So in physics, we don't have enhanced gauge symmetry here in this model. So our curve classes, as before, now are given by a class in the base identified with the section plus d times the fiber class. And those are our curve classes with this assumption. So there are more general cases which we're work in progress on, but I don't, not ready for prime time to describe that in detail. The shift by 3/2 is a shift of a curve class by 1/2 of C1. So here's where our sign problems are going to come up again. So C1 of P2 is 3 times a line. So we go ahead and now factor out the degree 0 contribution, and now we go ahead and write everything in terms of factoring out Q to the beta, putting all the fiber parameters in here. Again, here Q are the shifted coordinates. And the Ansatz is that Z beta is again a weak Jacobi form, weight 0. The index is beta times beta minus C1 over 2. This is an intersection in B, intersection of two curve classes in B, with multipliers corresponding to the shifted coordinates. And this is just the arithmetic genus of a curve in the class beta minus 1. So that was minus 1 in the case of P2, when we had a line. And then the formula is the Ansatz is that we have a weak Jacobi form. I didn't write down the weight and index. It's a little uglier than before. But I just said what the weight and index of the whole thing is. This expression we know has weight given by C1. Here we have C1 dot beta. We know the weights of eta. We know the weight and index of phi minus 2, 1. We can go ahead and count. And so this is completely determined by what I said before. So we have a determined weight and index, and in particular, this is in a finite dimensional vector space. So we have that. One thing I want to say here is in the Castel nuovo argument, this term is understood by this factor will correspond to the degree k coverings. And this represents the fact that we don't just have smooth curves, we can have curves with different components, and that we can have some of them in some classes, some components in other classes. We need to go ahead and look at all the homology and put the multiple cover factor everywhere we possibly can to go ahead and match the geometry. And this was also obtained, this Ansatz also appeared from a gauge theory analysis with just this form of it here, not I guess that was done too in another context. This was done by a gauge theory analysis by Vafa and collaborators. Okay. So now I think the old stuff that was in the old paper, and now for newer things, I want to go ahead and see the SL2Z action acting directly on X without closed string mirror symmetry. I'll follow Kontsevich and use homological mirror symmetry to go ahead and see this directly on X. So we'll be using the open B model on X to go ahead and infer about the A model on X. That's what we're doing here. Okay. So we're describing this as autoequivalence of the derived category for elliptic surfaces. This was done by Bridgeland. In the S part of the transformation of SL2Z was done by Andreas, Curio, Hernandez, Raparis, and Yau. And I'm doing this in a slightly different language, but I want to just write this in more elementary terms without just giving the full power of the derived category techniques. So X is itself a moduli space of sheaves on X. So how does a point in X parameterize a sheaf on X? We take the fiber that contains P, and we take the line bundle in it given by P minus P0, where P is the point I started with, and P0 is the unique point where the fiber meets the section, which we think of as the origin. So this is a space of sheaves, and we want to go ahead and work with the space of sheaves to go ahead and construct a new sheaf by Fourier-Mukai duality. The way we would do this is by forming a Poincare sheaf. This is a normalized Poincare sheaf. It's the sheaf which over a point P and X gives us this one, where here I is the ideal sheaf. So we have a sheaf on the fiber product of X with itself over the base. And then we perform a relative Fourier-Mukai transform. And here's where our sign ambiguity comes in. So we pull back, so I guess I don't remember if I said this earlier. So I guess I had it here. You all saw it, but I didn't. Is that so to really make mathematical sense, we're not really going to be in a derived category because of the square root. We'll be talking about twisted sheaves, et cetera. Or you could just think of this as a formal calculation. So we pull back C1 over 2 to get so I also didn't put in, this should be from the second factor. Pull back from the second factor on X. And in the language of derived category, we take pullbacks, push forwards, tensor products where everything is in the derived sense. So here's a formula for how to take a sheaf on X, get a complex on X to a complex on X. And morally, what this means, it's not exactly correct as written, is that we take our complex of sheaves, tensor with this Poincare sheaf, twist by C over 2, and take its cohomology to get a complex morally. The T transformation is easier to see. This, again, the same multivaluedness that we had before, the C1 over 2. And we just, this is now a straight tensor product. So here what we see is we have a sign ambiguity in S and in T that will disappear when we take ST, as we'll see. So rather than give I think the proof of what I'm about to say using the derived category is a bit technical. And so instead of giving a complete proof, I'll just explain the idea by just computing what I want to the SL2Z on generators of the derived category. Okay. So the derived category is generated by sheaves on the section. So these are sheaves on P2 in our main example, and the pullback of sheaves from base. Those two kinds of sheaves, under our assumption, generates the entire derived category. Okay. And then to compute the S transformation, there's a simple formula. This was essentially in closed form in paper of Yau et al. I referred to before, is that if you go ahead and take a sheaf supported on the exceptional divisor, its transform is a pullback to the whole space. And if I go ahead and take the pullback of a sheaf, its transform is supported on the exceptional divisor. And here I'm using standard derived category notation that -1 means shift one place to the right in the derived category. So turn a brane into an anti-brane here. So what you can see here just quite immediately is that if I take S and compose with F, all I do is I shift by 1 to the right, no matter where I start, because the C1 over 2 and the minus C1 over 2 cancel. And this is the reason for the shift. So if I would go ahead and take a formula before what we had, and I shifted, I didn't do the shift, I would take S squared, and I wouldn't just get a shift, I would get a shift in the tensor product with the canonical bundle. So I have to go ahead and take the square root of that to go ahead and make this possibly be an S transformation. And that's the geometric source of the modularity. So now, if instead, if I want to go to K-theory and just think about the charges of this object of the derived category, S squared is minus 1 on the nose. So it really looks like an S transformation. Okay, now to look at ST. Here this calculation is a little more intricate. I'll just summarize. If we take O of E, what we need is if we take the line bundle O of E and restrict it to E, that's a line bundle that can be identified because this is just the normal bundle of E, and the normal bundle in the Calabi-Yau is the canonical bundle. So again, we just get our old friend, this shift by C1, which just plays a important role in here. So if I want to compute ST of F, this is a sheaf on E, T will go ahead and first just take, I'll tensor with E, which will shift by minus C1, then I shift by plus C1 over 2, and I just get a shift by minus C1 over 2. And the S transformation on the sheaf on E, I computed before. That's right here. We tensor by plus C1 over 2. So I take this sheaf, I tensor by plus C1 over 2, and pull back, and I just get that. So the calculation is very easy. This one, the answer is easy to state. This is a little bit more involved. I need to use cones in the derived category, but never mind, the answer is just easy to write, similarly easy to write down. So if I wanted to go ahead, so I've already computed ST squared now applied to this. So ST gets me here, another ST gets me here, and now I apply one more ST, but notice if I apply T, what happens? T started with, I tensor with E and half of C1. So I will tensor with E and half of C1. So when I tensor with E, that kills this. Then I tensor with half of C1. So to apply ST, I have to apply S to pi star of F tensor half of C1. And what that does, we just undo the C1 over 2 and shift to the right. So what we just get is if we compute 3 shifts, we just shift 1 to the right. And then you do the same calculation one more time to apply to this, and we just get that on the whole derived category. So when we pass to K-theory, we just get this ST cubed is minus 1 on K-theory. And notice that when we take ST, that when we take ST together, this ST is clearly well-defined. There's no C1 over 2. So just like in our multiplier system, ST is a well-defined transformation on the derived category. So what we get is that we get this intrinsic SL2Z action on the even cohomology, which is the K-theory, with multipliers, which will be exactly absorbed by this, this power of eta. Okay. So now what I'd like to switch to is how to understand the Ansatz. Now, for this Jacobi form Ansatz. So if this is correct, I've given lots of evidence for it. The evidence is not really so much from enumerative geometry yet, but lots of evidence from the physics. So to go ahead and compute degree 0 invariance, we can also compute this because we're computing BPS invariance in the fiber classes and multiples of the fiber classes. And so here, these are computed actually with Yokonobu Toda with mathematical rigor computed this. There are methods in physics for computing these as well, but fortunately the mathematical proof agrees with this. The Euler characteristic of an elliptically fibered Calabi-Yau threefold of the type we're discussing is minus 60 times C1 squared. So C1, I'm dropping the B, that's C1 of the base. This is a characteristic number. So for P2, this would be 540. So from this, we know these BPS or Gopa-Kumar-Vafa invariants, and then that helps us determine Z0 and all the FGs at degree 0. So in particular, for the FG once genus is at least 2, we get this familiar expression. This, I apologize, I don't remember. This has appeared in the literature many times. I didn't cite this. It's in many places. So we have, in terms of these Eisenstein series and some numerical factors, and this P1, the C1 squared arising from the Euler characteristic, we get a formula for the F0G. And one thing to notice is that these Eisenstein series are usually modular with one exception. And the genus 2 invariant is actually quite interesting, and taught us a lot about this. So the thing about genus 2 is, in particular, the genus 2 degree 0 invariant is C1 squared over 96 times E2. So if we're going to go do holomorphic anomaly, we change that to the modular and non-holomorphic quantity C1 squared over 96 E2 hat. Okay, and now let's go to the wave function. Well, I guess the wave function version of the holomorphic anomaly. So this is the partition function with its full T star glory. We have coordinates z on the moduli space. So I'm just doing now a general holomorphic anomaly, not just for an elliptic vibration. The G is the Zamolodchikov metric, C is the Yukawa couplings, K is the Kähler potential, and this is what it looks like back in terms of the string coupling constant that we had before. So then, if we calculate the metric and the Yukawa couplings at large complex structure, and we conclude that in the shifted coordinates, there's the shift again, the holomorphic anomaly equation looks like this. Okay, and this almost looks wrong, right? It's supposed to be beta squared, like beta times beta minus C1, isn't it? Right? You expand this, beta squared minus C1 beta plus C1 squared over 4. C1 squared. Where have we seen that before? So the C1 squared over 4 so tau 2 is before is the imaginary part of tau. If we now rewrite in terms of our almost modular forms, we could then trade tau 2 for E hat, because these are now expressions in almost holomorphic forms. D by D E2 hat makes sense, and this equation is satisfied. The C1 squared gets absorbed in here, and we just get that expression which we saw before. I also took the liberty of switching. We have pi factors which disappeared because lambda is 2 pi z. So we have a pi in going from tau to E2, another pi here, and 2 pi's here, and they all cancel out. And that's why there are no pi's here. So this is the equation, and when we go ahead and take our holomorphic limit, we get this equation for the holomorphic partition function. And now this expression, this is fairly well known in the theory of Jacobi forms, that this, together with modularity, which is argued from the SL2Z transformation, implies that ZD is a Jacobi form of the claimed weight and index. So that's our argument for that. So to go ahead and finish justifying the Ansatz, we have to explain how do we get this. I mean, there's infinitely many meromorphic Jacobi forms of a certain weight and index. There's no control. So we want to see that we have this expression in terms of weak Jacobi forms. Okay, so we start examining the pole structure. And we have Gopa-Kumar-Vafa formula for writing the partition function in terms of the the BPS invariance. And when we write this, we see that the only poles that we get are at genus 0. The only poles in Z, only poles in Z come here. They're at Z equals 0. So in the modular language, when Z becomes a coordinate on a torus, they're M torsion. These are M torsion points of the torus where M has to divide the homology class. That's this multiple cover formula. Okay. Okay. So we have this multiple cover right there, and so we learn that the only poles in Z are at the torsion points. So just to simplify the explanation, let me just come back to P2. So we have Q to the D had the pole of order 3/2 D because of the shift of coordinates. It was just a fictitious 3 to the D halves factor that just got put in by a change of coordinates. So to go ahead and make this quantity well-defined, we have to have a pole of the same order in Z to the D to compensate. Did this just die? I think I saw another one here. Okay, so there's another pole of order 3 to the D halves in there to compensate. So we have poles in Z, and we have poles in Q. This is a Jacobi form, a weak Jacobi form, that has a 0 right where we need it at Z equals 0. Eta has a 0 where we want it. So when we multiply Z by eta to the third D and all these phi's, we do everything we want. We kill the poles coming from the Gopa-Komarov-Alpha formula. We kill the artificial pole that we put in by the change of coordinates, and we make this an invariant expression by killing the multiplier system. So I said eta to the 12th. I could have just as well said eta to the 36th. But maybe, okay. So all of a sudden, this is a Jacobi form, which is holomorphic in tau, and Z is in tau and in Z, and in Q it's holomorphic. That's a weak Jacobi form. So this expression is a weak Jacobi form. So as an anticlimax, let's call that Q, let's call that phi D, and there's the formula. Anyone want to shoot that down? I mean, there's some things here, there's no mathematical proof of this whatsoever. These are taking arguments that are well accepted in the physics literature. We get some very very powerful claim here, which we finally feel like we understand pretty well now. Okay, so to describe work in progress, we're working on refined SL2 times SL2 BPS invariance. Okay, so what does that mean? There's no U1 here, but one can imagine that because of the elliptic vibration structure, there's some symmetry. Maybe refined invariance makes sense here. We don't know, but it will either we can't lose. It will either work or it won't. If it works, we'll learn something about the refined invariance. If it doesn't work, we'll just see that the refined invariants aren't really invariants, right? They can change under changes of complex structure, but we'll see something interesting out of this part of the project. I'll report on that later. We also can have more sections of E, more sections of the elliptic vibration, and this is related to E-strings calculations for DPN using the half K3. So Minchin, Albertin, Perechkin, or Maximilian, working on that. And then what we'd really like to do is to look at more general elliptic vibrations where we could have enhanced gauge symmetry, we can have different components. And this is going to be, the monodromy structure is richer and more interesting, and I don't know what that's going to look like in the final analysis, because we'll have both this SL2Z, and then we'll have Seidel-Thomas twists about these extra divisors. So there's some really rich structure that we're trying to tease out in this context. Okay. Here are some refined invariants that we found so far. So what these are, we don't have the full partition function, but we can take find the FG and refine versions of the FG and match geometry. So these calculations can be done by both the algebraic geometry using Joyce's way of computing. And conclusion, I'm going to finish on time, I think. So the partition function of an elliptically fibered Calabi-Yau can be described by Jacobi forms. And now I'm quite satisfied with our understanding of this on the physics side, and I'm quite dissatisfied by my understanding on the mathematical side. Thank you.
Please wait for the microphone.
Hello? Okay, so I have a question. So when you compute the Gopokumar-Vafa invariance, let's say pair invariance, you use the MNOP correspondence?
No. So what we're doing, so there's very little mathematics that's actually proven here. What we do is I use formulas to go ahead and compute the BPS invariance. So I'm usually computing BPS invariance. I could be using torsion sheaves, or I could be using PT invariance. I don't need,
So these PT invariants that you have computed, they are not coming from functions which satisfy some sort of...
I'm sorry, I didn't hear?
They are not coming from functions, equations, such as holomorphic anomaly.
No, they're very I calculated lines in P3, in P2, and I calculated lines meeting a fiber. It's just, the calculations are really, really very, very simple when we can do them, and the structure gives all the power there. Now, I do use some more sophisticated techniques to go ahead and check the other numbers, but that's not, that's really just to keep us honest, to really believe what we're saying.
But you're not predicting holomorphic anomaly for DT?
No, we're using the holomorphic anomaly to justify the Ansatz.
Other questions?
So to get the refined invariance for the compact case, you also use just the holomorphic anomaly equations?
So there, on the geometric side, what we're doing is we're computing moduli spaces of branes, and then in cases we're assuming that the orientation data of Kontsevich and Soibelman is the most natural one that you can write down. So there's nothing coming from the physics or the geometry to really specify what the orientation should be. I mean, this is the part that we just don't know if this is well defined. So we do that geometrically to go ahead and compute these numbers, and then on the physics side, we go ahead and take the formulas for the FG that came behind the scenes about working on the partition function in the unrefined case, and then making natural ansatz about how that seems to naturally refine. Okay. Did you want to add anything mentioned to that? Yeah, that's okay.
He'll get his turn. Okay, let's thank Sheldon again.